So this is the either benzoic acid or orthotoluic acid. I want to do characterize it now by getting the mass of it. The way I'll do that is I'll get another watch glass and get the weight of it and scrape the solid carefully off the filter paper onto that pre-weighed watch glass. After I have the weight of it, then I will take an IR and NMRs of it. So let's get another watch glass. So I want to zero my scale again. Looks good. Add my watch glass. And record its mass empty. So it's 73.2996. 73.2996. I'll write that down right away. This is the aqueous precipitate. Empty watch glass. Okay, now let's bring that over to our impure solid here. And I will carefully scrape that off onto the pre-weighed watch glass. Oh, and I'll label this pre-weighed watch glass as well. Let me get the aqueous layer, aqueous precipitate, sorry. And this is me, MFS. Today is April 6th, 2021. Got it. I maybe could have weighed that after I labeled it. We'll have the mass of the Sharpie ink, which I think is pretty low. Now to do this, I'll get a new spatula, clean spatula, and tweezers. I did my dishes last time, so I got clean equipment ready to go. Okay, I've got my aqueous precipitate on the filter paper, my pre-weighed watch glass. Let's scrape it onto it. Oh, that came off as one big chunk. That was easy. Had plenty of time to dry. It's been over a week since I put it out to air dry. And that looks really good. I have maybe a small amount still left on the filter paper, but that's an acceptable loss to me. So let's go get the mass of this aqueous layer precipitate. I'm back at the scale, zeroed out. Got my aqueous precipitate, put that on there and see what it registers. When it was empty, it was 73.2996. Now it's 73.6346. I'll write that down. 73.6346 grams. Watch glass plus aqueous precipitate. And remember, as it's booting up, I'll show you a little bit more. We've got our zinc selenide crystal right there, that gold little circle. We're going to place the solid on there, and then we're going to crush it down with our anvil to get good contact. The infrared light's going to come through the instrument into, it'll hit a mirror, bounce into the zinc selenide crystal, and do attenuated total reflectance. It's going to be bouncing through that zinc selenide crystal. The sample that's on the molecules on the zinc selenide crystal will absorb some of that infrared light. What doesn't get absorbed is hits another mirror in here, and then it goes to the detector, and the detector makes our spectrum. So before we run our sample, we need to do a background scan. It's been a week or so since I've used this, so I'll first double click the spectrum software to turn it on. Okay, now it's asking me for if I want to log in as an administrator. I do, so now I am an administrator. There's no password. And here we are again. The main area we go to is this instrument drop-down menu. I'll click on that and then I'll go scan the background. Before I scan the background, I should have checked to make sure the zinc selenide crystal looked clean. It was. So I scan the background. It'll tell me the parameters. I'll accept the default parameters. Click OK. And now it's going to do 4 scans. And it's going to be scanning the air that's right above the zinc selenide crystal, the air within this ATR adapter, the air inside of here, and then the internal components of the instrument. It's going to store that background and subtract it out from our sample run, sample scan. So this looks good. That's what our backgrounds are supposed to look like. I have a printed out version of it here. You can see it's looking good, very similar. And it's asking us to overwrite the last background scan. And I'm going to say yes. I'm going to get rid of the old one, keep the new one. And this looks great. I'll just point out a couple things again as usual. I'll turn on the vertical cursor, so you can turn it on by clicking it on. And there it is. This is the screen line here, the vertical cursor. And then you can click it off again and on again. And then, why would I turn it off again? I was going to use it. So I can move it over here. And as I move it, watch as I move the green cursor, you can see the value at the bottom changing. So there's a signal right here, for example, that is at 3,851.42 reciprocal centimeters. If I double click now, it'll label that for us on the spectrum. Got it, I can move it to the side. So that is water vapor in the air. This one here, double click, is a little less than 3,000. That's the sp3 carbon dihydrogens, and that's for the plastic inside of the instrument. And then this one in the middle kind of looks like a carbonyl, but it's not. That is carbon dioxide in the air. So I'm breathing out some carbon dioxide. That's about 2360 usually. And then we got a lot of other, I think this is mostly like plastic CH/CC bond changes. Stretches and bends. Okay, so this is good. I don't need to keep this. I'm going to delete this, so I just hit the delete key. It's deleted. And now I'll go over and put some of my sample on the IR spectrum. I've got it here, and I used the same spatula I scraped it out of the off the filter paper with. Bring this over. Set that right on the zinc selenide crystal. And that is much more than I need, but that's okay. I've got a lot. And when I clamp this down, if I try to run the IR right now, it won't come out good because it's not getting enough contact with the zinc selenide crystal because it's solid. But what I do is I clamp it down, and I have to clamp it down hard, strong, all the way down like that. Boom. Now, the thing a lot of times students, when they run this, they don't clamp it down enough and their spectrum doesn't come out good. The way it works with ours is if you look at the top of the anvil, see how it's got the copper colored and then it's got that stainless steel. You have to almost completely bury the stainless steel in the housing there, like all the way down. Yeah, and you twist it with about the torque you would twist what's now called an old-fashioned car key ignition. So you twist it and then it should be good. And if it's not good, we'll just rerun it. But I think that's going to be good. Let's see, it looks like it's pushed down on there pretty good, huh? So let's go run it. So I'll come back over and I will go to Instruments. Where are you? Instrument. Scan sample, not background this time. And it says scan. I say OK to the default parameters. A lot of times students make an error when they want to scan a sample. They accidentally hit scan background. And then the next sample that's run, it's subtracting all that sample's signals from the next. So, oh, look at this. Oh, yeah, this one, it's either benzoic acid or orthotoluic acid. Can we tell? That's actually IR, won't be as easy to tell on this one. But I definitely think we have carboxylic acid, and this spectrum looks great. Yeah, this looks really good. So let's label some peaks. I can label like the outside here. What is this guy starting at? It's just over 3,000. Oh, that could be the benzene ring CHs. Let me actually draw these out real quick so I can refer to it directly. Okay, here are the two potential acids. It's benzoic acid, and orthotoluic acid. Orthotoluic acid has just a methyl ortho to the carboxylic acid. If our carboxylic acids are a reference, we call that the ipso carbon. The carbons right next door are ortho, the next ones are meta, and the final one here is para. So that's orthotoluic acid. And in the IR, the difference between these two, well, let me say what's similar about both of them. Both of them have the OH of the acid. They both have that signal, which I have it up here actually. The acid OH is a big mess from like 35 to 23, right? And they both have a carbonyl as well. So the carbonyl, where does those show up? About 1700. This carbonyl is attached to a benzene, so it'll be less than 1700, probably like 1660 or so. Okay, so we got that. So they're similar that way, and they have another thing in common. They each have sp2 carbon to hydrogen signals. Okay, they each have that, and those sp2 carbon to hydrogen signals, they show up a little over 3000, like 3030-ish. But the orthotoluene has one other signal we've memorized that the benzoic acid does not. It is, which one? The sp3 carbon to hydrogen, these guys right here. So if we can see an sp3 carbon to hydrogen signal, then we could say, oh, it looks like we have orthotoluic acid. Because the benzoic acid has no sp3 carbon to hydrogens. And the sp3 carbon to hydrogens, they show up around 2980, a little less than 3000. But the problem with this molecule is its OH also overlaps that region, so we might not be able to tell if we have the sp3 or not. Let's check. So I've got a signal a little over 3000. That might be from the carboxylic acid, or it could be from the sp2 carbon to hydrogen. And then if I come to the very end here, that's at 25. That's probably, this is the alcohol, the OH of the carboxylic acid. Let's look around 3000, a little less than 3000. Let me see, where am I at? I'm at 26. That's 28. Ooh, that might be it. This signal right here might tell us that we have orthotoluic acid and not benzoic acid, but it's hard to tell because the rest of this is from the OH of the acid. So, oh, it could be this one too. Never mind, that might be it. Or maybe both. They're both pretty close. So this might be orthotoluic acid. It might be benzoic acid. I'm not sure yet, but we're going to do NMR, and we'll know after we do NMR. So let me now label the carbonyl. It's a little less than 1700, as I told you, because when you have a carbonyl attached to a benzene ring, it almost pretty much always goes less than 1700. So, but that looks pretty good. And we have a lot of other signals here in the fingerprint region. Maybe I'll label that one. And then this one is sticking to the bottom. I don't like that. I'm going to actually squeeze this spectrum a little bit. Let's do, so what I have to do is I have to tap the top of the screen and the bottom of the screen. And I got to say the right word. I got to say easy, cheesy, Georgian wheezy, squeeze me, squeeze me. Oh, see that, did that? Yeah, no, that's off the bottom. That was it, it was the top. All right, so we got it. I can label that one. Why not get another one labeled? And as always, I'll add a text box. This is my aqueous layer. Precipitate. And I'm always want to put the date, 4/6/21, and my initials. Okay. Got it. Now I'll take a picture of it and I'll print it too. I think sometimes when I don't like printing if I don't have to, but I think if I print it and cam scanner it, it looks a lot better than if I just take a picture of the screen. So I'll print it. Yeah. So let's get this clean the proper way. I'll grab a chem wipe, squirt it with a little bit of ethanol, and try to grab off the majority of that benzoic acid derivative. And I'll remember to also clean off the tip of the end here. I'll do that a couple times if it's coming off clean like it is now. And then after I do that, I'll do a dry chem wipe. When I was trained to use this instrument, they said not to use chem wipes to clean this, but I don't know what else to use. But it feels like the instrument works well, so I don't know. Maybe the zinc selenide crystal would last a little longer if I didn't use chem wipes. I don't know. Maybe someone in the YouTube universe will tell me. So I got a couple things here. I got a test tube that I'm going to initially dissolve my aqueous precipitate in. I labeled it aqueous layer precipitate for NMR, my initials and date. And I have an NMR tube after I've dissolved some of that solid in an NMR solvent. Then I'm going to transfer it into my NMR tube. And I've labeled that too at the, it's hard to read, but it's on the, I did it with pencil here, aqueous precipitate. I have to measure a couple things before I start because I want to put just the amount of sample in here that I need, and I want to be as concentrated as possible. Our NMR is great. I don't want anybody talking down about our NMR, but it does have a really weak NMR magnet. It only has a magnet strong enough to make a 60 megahertz NMR. Because of that, we just need to make our samples really concentrated as possible. We don't necessarily need them so concentrated for proton NMR, but to get good carbon NMRs we do. So the way we do this is we take and we measure from the bottom of our big test tube, our 13 by 100 millimeter test tube. I'm going to mark a line at half a centimeter from the bottom. I'm going to set the phone down for this. Okay, so I marked a line on my test tube, my 13 by 100 millimeter test tube, at about half a centimeter. See that there? Okay, and then on my NMR tube, which is much thinner, I marked a line at about 4 centimeters. Yeah, right there, that 4 centimeter line. So what the thought is I'll prepare my sample here, and I'll make the volume reach that half a centimeter in the greater diameter test tube. And that, when I transfer it, it should fill this thinner tube to about 4 centimeters. This way, I'm not creating, so let's say instead of just going to half a centimeter, I went up like 2 centimeters or so, then I would only use a small amount of it for the NMR, and I'd be wasting the expensive NMR solvent. I don't want to waste the NMR solvent, so I want to use just the amount I need to make the most concentrated sample I can. So let's move over to the scale and start doing this. So what I'll do is I'll take a beaker, small beaker, and the test tube, the 13 by 100 millimeter test tube, set it in the scale and zero it first, and then I'm going to be weighing my aqueous layer precipitate into that initially. This aqueous layer precipitate would be hard to get into this test tube, and if it didn't all dissolve, it's hard to deal with, so I always want my students to first do it into a big test tube. And so let me zero this out. It's looking good. And now how much do I add? I aim for about 0.1 grams if I have it of the solid. So I think I have more than enough of that today. So I'll pull this out. I won't add it while it's in the scale. I'll add it while it's outside of the scale. And I'll start adding some of my aqueous precipitate. I gotta break it up a little more, huh? Try a couple big chunks like this, see what that does. Put it back into the scale, and we are reading about 0.03, so I need about 3 times as much of that. So I'll add a couple more big chunks like that. My thought is I won't be able to dissolve all this, but I want the solution saturated. And if I do dissolve it all, I've still got more solid here I can add. 0.809. Add a little more. I'm always adding this outside of the scale as usual, right? Keep our scale clean. Our most stolen piece of lab equipment. Most often stolen. Okay. Back over here. That's close enough. I've got a couple NMR tests, NMR solvents at my disposal. I have our most common one, the deuterated chloroform. It's 99.8% isotopically pure, so it's, and it has TMS in there, our reference for us. So this deuterated chloroform, CdCl3, it's 99.8% that, but it's 0.2% CHCl3, the H1 isotope. This is what we'll use for most everything. We'll try this first if it's an important molecule and we feel like it's big spending, we'll get the deuterated DMSO, deuterated dimethyl sulfoxide D6, 99.5% isotopically pure. So this is deuterated DMSO. This is much more expensive than the deuterated chloroform. So I only use this on special occasions when I want to order bottle service in the VIP room. So we're going to do that today, but I think I'm going to be using this. But what I like to do is, since this is so much more expensive, instead of just using this expensive stuff alone, I will first try the deuterated chloroform, the less expensive, but still pretty expensive. And if that doesn't dissolve at all, I'll start putting some drops of the good stuff in there to see if that helps. Let's start with our deuterated chloroform. Does that look, can we read that? I don't know, is it? Yeah, believe me, deuterated chloroform. And I'm going to add less than to the 0.5 centimeter line and see what it looks like. First I'll draw up some deuterated chloroform and push it back in. This is a pipette that's just for this bottle, should be clean. Add that deuterated chloroform. Oh shoot, I added too much. Rusty. I added over 0.5 centimeter and it all dissolved. That was dumb. Wasteful. Oh well, it's okay. It's been a year since I've run an NMR. So, I don't need the expensive deuterated DMSO at this point, but I don't have a saturated solution. I want a saturated solution, so I'm going to add more of my solid to this. Let me go get some more solid. I brought over the solid, and I'm going to add it to the NMR solvent until it becomes saturated. That dissolved. And I'm okay with doing this. I don't feel like I'm wasting my solid right now because I can get this solid back by just evaporating the deuterated chloroform. If I add the DMSO though, the deuterated DMSO, it's much harder to get back. It's got a higher boiling point. Okay, it's not saturated yet. Yeah, see, this was silly of me. If I was more careful, I would have added half as much deuterated chloroform, and I wouldn't have to add all this solid. But that's all right. We all make mistakes. I was probably a mistake. Okay, I think it's getting closer. Still dissolving pretty good though. I may have to just go with it. If I really want to have it saturated, what I could do is evaporate some of the deuterated chloroform that I over added. Getting there. My camera. Yeah, I see some. It's looking. Oh, Oh, it looks like it's all dissolved still. But it's going to be pretty concentrated. I think my goal is to get a great proton NMR. That's going to be the easy part. But in the carbon NMR, I'd like to get every carbon signal. Even the quaternary carbons with no hydrogens, the shortest ones, I want to see those too. That's why I wanted to make it nice and concentrated. It's either saturated or near saturated. I think I see little particles in it. And I'm going to go with this. So what I'll do is I'll pipette in that with a new pipette into my NMR tube up to the 4 centimeter line, and I will be more careful about it this time. But actually, if I go over the 4 centimeter line, it's not that big of a deal. But under is not good because then it might not catch all the radio waves. So there we go. Looks good. I'm ready to go. So I'll cap this. I chose blue this time. Okay, and I'll put this in the NMR and we'll find out what we got. Okay, I got my NMR tube. I'm going to try to stick it into the top of the spinner. Yep, there it is. And I'll adjust the height of it. The depth gauge. Push down until it stops. Stop. It should be at a good height to spin. It spun really well last time. Hopefully it still spins well. Put it in here. It's floating on the air. And then I'm going to press the off button and it'll fall down in. So off. Down it went. And now I will try to watch the cap and see if it spins when I turn the air back on. It did. Looks good. Having a good spin day. Because I'm the spin master. I'm the spin doctor. Close that up. I could have closed that a little gentler. And come over and let's run the, as always, first do the Proton NMR. Proton NMR first because we'll get not only the spectrum, but we'll get to shim if we need to and set TMS to 0 if we need to. And we start off with the AII NMR software. And it's in the Proton NMR setting, so that's good. And I just type ZG, enter, and it's going to start pulsing all the radio waves of our hydrogens, and they're separated into their alpha and beta spin states because of the magnetic field. And the alpha ones can be excited to beta, absorb. It looks like a weak FID, but that's actually okay. The methyl salicylate I ran just before, that one was very concentrated. So let's go to nuts and see how this looks. So this is the methyl salicylate still. The command to bring it over is the letter A and the number 2. And there it is, yep. It's looking okay. Looking a little rough, not too concentrated. See these? This baseline looks pretty rough, but let's see what we got anyhow. Let's assume this is TMS right here, and I'm gonna left click and hold and then type the letter M on the keyboard, and that will give me every peak above that horizontal red line will give me a value for it. So the TMS, which I think is the TMS, is at 0.525 right now. So let's fix that first off. Let's go over to AII, PNMR, and type the command FO for frequency offset, and hit enter. Where's our current reference point? It's, I forgot already, 0.525. So I can enter that in, 0.525. Say okay to that. Where do I want TMS? I want TMS at 0. Hit enter. Now I need to rescan again, so it's just ZG, enter. And see how it looks. Yeah, this one's looking pretty dirty. I think I'm gonna fix it. But we'll get the dilute spectra first, just why not? Okay, it's done scanning. I'll bring it over to nuts. And the way I bring in the new data is I type the letter A and the number 2 and enter. Did I do it? Oh, I did, yeah. So now the TMS is much closer to 0. If I zoom in on the TMS by double clicking, dragging, and right clicking, it's not looking like a singlet, huh? So this tells me I need to shim. So let's go back and shim now. In AII PNMR to shim, you just type shim, S-H-I-M, hit enter. It's gonna ask for relaxation delay. 2 seconds is what we use. We hit OK, and we let it shim. While it's shimming, I can look back at that last spectrum. We can tell already what we got, which is nice. So even though it needs to be shimmed, it's not looking too pretty. The signal over 12 parts per million tells us we have the carboxylic acid, which both of the possible carboxylic acids, both of them are possibly carboxylic acids. Here's their structures again. So we have the carboxylic acid, okay. We have some aromatic signals between like 7 and 8. That's good. And then we have this signal over here, a little past 2. What does that suggest? Does that suggest it's benzoic acid or orthotoluic acid? It's looking like orthotoluic acid, that 3 hydrogen singlet there, the methyl. That's probably what that is. So once we've shimmed it, we'll do the, we'll rescan, bring the FID over, and then we'll integrate. That'll even tell us more. Okay, so it's done shimming. It's no longer pulsing. So I'm gonna rescan. As always, ZG, enter, enter. Wait for it to come up. Okay, the FID looks stronger. I didn't point it out before, but I should have. The receiver gain before was at 3, and it during shimming adjusted to 5 because it's a more dilute sample. It's basically like a hearing aid. The hearing aid was turned up so that it could hear more dilute samples. Okay, let's go back to nuts and bring it over with the same command again, the letter A, the number 2, and there it is. It's looking much nicer. I can zoom in on TMS, see how it looks. Yeah, it's a singlet now. Remember how it was not a singlet. And then we've got this singlet as well for, I think, the methyl of orthotoluic acid. The aromatic signals, they're a mess, but that's normal. And the carboxylic acid, looking good. So let's go down our list of what to do. We've got it shimmed, we've got TMS to 0. We should zoom in on our peaks and then text box integrate print. So let's zoom in on our peaks. I'll show you. I'm back in the base level again. It's been a while since we used this. See how it says base level there? To get into the zoom subroutine, I just double click anywhere. It says zoom. And then if I drag a box over the area I want to zoom in on, let up that drag, right click, and I'm zoomed into that area. So I like this. But I'm still in zoom. I want to get out of zoom. So how do I get out of zoom? Hit enter. Hit enter, it gets you out of everything. Back on the base level. Now I want the text box subroutine. Does anybody know that command? Anyone know that command for text box? No? Did someone say no? Yeah, that's right. It's N-O. And now we're in the enter notes or text box subroutine. And to add a note, we type the letter A. There it is. So now I'll type in, this is aqueous layer precipitate extraction lab. MFS, today's date 4/6/21. Okay. Okay, on that, move that over here, say. And then these peak labels up here, I want to get rid of those, but I'm still in the enter notes subroutine. I got to get out of that before I do anything else. I don't like to be in more than one subroutine, so hit enter, back in base level. Okay, so I'll just say do a few of these. I'm going to click and hold and type the letter M. Yeah, that's pretty good. Oh, so now my text box is in the way of that. Let me go N-O again. I'm back in enter notes. I can move it over and enter to get out. There we go. Okay, now I just want to integrate. And the way you get into the integration subroutine is you type the command I D. And the integral curve popped up right when I typed the D of the ID. And I want to chop it up around each signal. So the way I do that is I go to the left of a signal and I double click, and then I go to the other side and single click. And then over to this next signal, double click, single click, double click, single click, double click, single click, double click, single click. Wait, that's TMS. Why am I integrating that? I'm going to get rid of that one. I can get rid of the last integral cut by typing the letter L. Boom, it's gone. Now I want to set a value for these. So if this is this one over here is my 3 hydrogen singlet for the methyl, I want to see if that works out with these other ones. So let's click once, and I've got the red line, and then I go over and I type the letter V as in Victor, and it says right now it's set to 0, but I'm going to set it to a value of 3. That'll be my reference point. I'll type OK. Oh, yeah, and this looks great. Really good. I've got the 3 hydrogen methyl signal. You look at our orthotoluic acid there. 3 hydrogen methyl. Then the aromatic ring should have 1, 2, 3, 4 hydrogens. 4 total, right? Because the methyl's taking up a spot. Here, let me write it down for you. So we have the 3 hydrogen signal here, right? 3 hydrogen singlet. And we got of course, the 1 hydrogen acid signal. And then we have 1, 2, 3, 4 signals around the aromatic region. So our integration is very good. 3 for the methyl, 3 and 1, 4 for the aromatics, which they should be 4, and 1 for the carboxylic acid. This is great. So let me try to print it. My printer might not work. The first time you use it in a while, like the ink cartridges are like funky. Let's try. To print, I just type the letter P. And it'll ask me to click OK the first time. Okay, let's see how it goes. The printing didn't come out great, but that's okay. I decided I won't use the printing this time. I'm just going to, I used this snippet tool, and I snipped it out and I emailed it to myself. So yeah, that turns out to be pretty good.